So welcome back once again in the second part of the topic on which I was talking about the basics of GNSS and NavIC. So just similarly, once again, let me start where I have stopped. Okay, now. So we talked about GNSS. We are talking about GNSS user segment. So different types of receivers. Some of them are very costly. Some of them are very cheap. For example, this one would cost you around 20,000 US dollars. So this and this. So this is the antenna and this is the receiver. And uh, this one will cost you around say what I can recall, that is some $5 to $10, $10 to $15. So you can very well understand that how the cost differs. Obviously, when the cost differs, the performance and the capability will also differ. That will be covered in large detail, and specifically during the hands-on, we will expose you from where you can get it, what are the price lines, etc., etc. So now a bit detail into the science of GNSS, the GNSS measurement. So inside the receiver is electronic device. There are so many electronics inside. So for the time being, let us let us keep it as a black box. Okay, so it's a black box. Inside it, there are a lot of electronics, and externally, we have an antenna which is put generally in an open view of the sky, that there is no obstruction outside the room, and from there we take a cable and connect it with the receiver. Or in real life application, generally there may be embedded antenna. So it's a blocks inside the box. On the top of the box, the antenna is already fabricated there. So what they actually measure, what this electronic system actually measure. Okay, so you can see two different types of radar lines. One, a digital line, and another one is an analog line. So actually they get digital data in the forms of zeros and ones, and at the same time they carries the signal, the information, the satellite. Already I told that xi, yi, x1, y1, z1, that has to be transmitted to the antenna for calculation, or to the receiver system for calculation. That's why they are generally embedded on a carrier frequency. The carrier frequency for most of the GNSS system lies in the L band of frequency. That means between 1 to 2 gigahertz. Okay, we call them in different names: L1, L2, L5, etc. And in case of NavIC, along with L, there is the S band, what falls in between 2 to 4 gigahertz of frequency. Right. So they measure pseudo-ranges through code. So we call this type of pattern a code. That means here may be two ones, then a few zeros, one, two zeros, one, like that. So we use pseudo-ranges. We made the Doppler. We measure the Doppler. As because the satellite is moving, as per physical law, the satellite cannot remain static, it will move. Okay, I will, for the young ones, I will, at the end, I will ask a question, why it should move. And secondly, the GSO, for the young researchers, not for the faculty members or others, or the students, why, if it need to move, if there is no relative motion for the geostationary Earth orbit, how the first condition is satisfied. Okay, so as because it's moving, so there would be a Doppler shift in frequency. It's a very common term. If you need some more clarification, I will tell afterwards. We made the carrier phase. That means, so the carrier frequency is coming. What is the phase of the carrier? That means, what is with one state it is reaching the receiver. That is a very unique measurable quantity, and we use it for our own purpose. Then carrier to noise density, that what is the signal strength, whether it is 30 some unit or 40 some unit or 50 some unit, like that. These measurements are raw measurements. Most receivers generate single point navigation output, position, velocity, and heading. Heading means in which direction, which is the north. Measurements on all channels simultaneously, generally, as because it has to measure so many parameters. So a receiver generally has more than one channels. I'll come to that afterwards. More than one channels, and each channels generally track one particular satellite. So we are seeing right now, for example, we are seeing 40 satellites. we are operating all in view mode, that we are using GPS, GLONASS, Galileo all together. And so in the satellite receiver itself, there would be 40 channels. Each channel will handle the data from one satellite. That's the basic structure. I think some of the experts will tell you more about the rather receiver architecture like that. The time at which a set of measurement is collected in a data epoch, it is called GPS time. And the data rate, that means very slow data, 50 times per second. In terms of digital communication, it's very, very low data rate, 50 bits per second or 50 bps data from the satellites. It is transmitted to the receiver. The receiver take the data, finds out, uses all these parameters, and after that gives out your location. Now basically to a bit more complex, but it is required. There are two types of measurement. If you can recall the basic equation, that on the left hand side we have got R. R means the range. So to measure the range, we have to make some measurements. That means we have to find out the distance between our antenna and the satellite. It is done in two methods. How? The first one is this method. So we calculate. So this signal is transmitted, this particular code, that means a digital signal, digital data, it is transmitted from the satellite. Okay, it is received at the receiver clock here. So what is the time difference? That means how much the receiver clock should be shifted so that we get one-to-one correspondence with the two codes. To be more specific, each of the satellite transmits the code of the each satellite. It's different in case of GPS. If you take the GPS example, in case of GPS, the in case of GPS, each satellite transmits in different codes. So, for example, this is the code transmitted by satellite number 2. Out of the 27 or 30 satellites, it is code number 2. So, what our receiver does, receiver knows all the codes. Code for number 1, code for number 2, code for number 3, like that. So, now the receiver tries to match the codes with that received code. So, one of them will match. For example, number 2 here will match. And now the receiver will time shift the code, this one. The receiver will time shift the code with the original one, that how much it has shifted during its transmission. So the more distance it will cover, the more will be the shift. So by this way, the receiver can measure the time of travel. That is called a code-based measurement. Okay, so the code-based measurement is used to differentiate satellite signals and to provide signal timing information for range measurement. Code-based results are unambiguous, very good quality, but precision is limited. If we use a code-based measurement, the maximum precision of solution. So I will next in the discussion session, I will talk about precision and accuracy, which is needed again and again. So the precision of the solution, it remains within order of few meters. So if I use a code-based measurement, finding our own location, the error would be say plus minus 1.5 meter. Okay, so nearly 4 to 5 feet. So I can be anywhere in a circle of 4 to 5 feet. For many applications, it is quite good, and people are satisfied with that one. Right. So code-based measurement, but the advantage already we have written, that it is unambiguous and very simple to do. That's why in many cases this is used. The second method, it is another method. That method is, if we can, so it is the carrier signal on which the code is there. If I go back a bit here, you can see. So this is the code and this is the carrier. So the code and carrier, so this is the code and this is the carrier. The code and carrier, they're mixed somehow. Okay, I'm not telling what is the exact method, and we are getting the output. So we have got two parts. One is the code, another is the carrier. Right. So here, if we can measure the carrier, how many cycles of the full carrier, and what is the phase of the carrier here? Right. So for here, the carrier has started. So this is one full cycle. This is to number 2 full cycle, number 3 full cycle, number 4 full cycle. So if I can measure the number of carriers, so multiply it by the wavelength of this carrier, say 19 centimeter. In case of the L1 signal, so multiply it with the wavelength. into number of full cycles, how much it has taken place from here to here, and the part of the last carrier cycle. That means whether it has reached at here or here or here. So that much of distance we will add. So we will measure the distance much more accurately. Let me give one example. Suppose I want to measure the length of the room in which you are sitting. There may be two methods. You can take a measuring tape, right? A measuring tape of say 5 meter length, and you are measuring that one. The room is maybe 3.3 meters, nearly 10 feet, right? But now I'm giving you a smaller scale, say 30 centimeter scale, what we use in our day-to-day life for drawing the lines. So now if you measure the same length using the smaller scale, obviously you can very well understand it's very difficult. You have to measure it multiple times. But instead of 3.3 meters, it will tell it is not 3.3 meters. It is 3.311 meter or 3.31 meter. So you can very well understand we are getting one order of better measurement. But in the second case, the process is cumbersome and there may be errors. Suppose you are measuring your room using a very small scale. So you are counting 1, 2, 3, 4, 5 like that. And while measuring, you are missing 1. What should have been 7, you are measuring it to be 6. Or what should have been 7, you are taking it to be 8. So this is called cycle slip here. So instead of measuring n number of cycles, exact cycles, we may measure n plus 1 or n minus 1, which is very common. And we are losing some 19 centimeter or we are adding up some 19 centimeter. So that's why if we can measure the carrier phase of the carrier, we can have better measurement and we get one order of better accuracy. How good? Earlier we are getting meter level, now we are getting centimeter level. So when you are finishing your measurement using carrier phase based measurement, you will get a circle whose radius is maybe 10 to 20 centimeter. So you can very well understand that how fast your accuracy or the precision comes down to much a better solution. So this is the basic equation of code-based measurement. For the time being, I am leaving this one. So basically the idea is P is the pseudo range, C is the velocity of RF signal, delta T time of travel. So we get this geometric range. Along with that, so different correction factors. These correction factors will come not only our measurement error. Similarly, the carrier phase based measurement is based on the basic observation equation in terms of length. Although we are telling here phi, which generally represents a phase, but actually we are measuring, here also we are measuring distance, here also we are measuring distance. In the previous case, the solution precision is the order of meter. In this case, the solution is in the order of centimeter. So resolving or estimating the carrier phase ambiguity, already what I told, it's called carrier phase ambiguity. Whether I have measured 7 or whether I have measured 8, that is an ambiguity. So carrier phase ambiguity resolution or resolution, that is a key issue for carrier phase based measurement, GNSS measurement, which is of course very popular because of its inherent good quality solution. So next we will see how this is done. But before that, so what I have shown you that a set of 4 equations using which we are getting our solutions. So it's a mathematical thing. So if it is a mathematics, so always we should get a single point. Suppose we are plotting the solutions, what we are getting, this is the longitude in degree and this is the latitude in degree. So the longitude and latitude in degree, when we will plot them, it is expected that as because it's a mathematical solution, so mathematical solution, they will remain fixed. Although whatsoever may be their error, the precision may be 1 meter or few centimeters, but they should not deviate from a fixed point. But what we see actually what we see, if we plot those, we have taken some cases here. It is from one of our experiments. You can see some of the solutions are coming here. Some of the solutions are coming here. Some of the solutions are coming here. So but it confuses us. Why there should be a difference? The difference comes due to different types of errors, what is inherent in case of GNSS based measurements. So if you take this complete situation, so this is the complete geometry. So this is the GNSS satellites. So these are the GNSS receivers, and in between there are different layers of the atmosphere, ionosphere, troposphere, etc., etc. Okay, so already I told that okay, the satellite is giving us their own solution xi, yi, zi. If the measurement itself is in error, that may happen, because there cannot be a absolute measurement. Always there are measurement errors. So what actually the satellite is transmitting is xi plus delta xi, yi plus delta yi, zi plus delta yi. So we call them satellite ephemeris errors. So in a equation, if on the right hand side some of the known parameters they have got errors, so obviously the solution would vary, and most importantly the errors do not remain fixed. So instead of getting a single point, we get this type of scatter. Next, satellite clock errors. So the satellite clocks what are running, they also run in a relativistic effect. They have got their relativistic effects. So the satellite clock would be some very small, maybe order of few nanoseconds or less than few nanoseconds error. But when we are talking about millimeter level accuracy, I'm giving you a second problem to the students, that if there is a measurement error of 1 nanosecond, what would be the distance between the two measurements? Okay, order of 1 nanosecond distance difference. So what would be the difference between their position? Right. So you will find out yourself. And second is satellite geometry. Fourth is satellite geometry. Satellite geometry means how the satellites are scattered over the sky. More scattered satellites, the better. But nowadays, as because there are so many satellites, the satellite geometry is not a big headache for us. Now comes the main culprit. When the signal passes through the ionosphere, uh, you will hear about this more. Ionosphere is a layer of charged particles, right? So these charged particles keeps on varying. Number of charged particles, their density, their numbers, and their location, they keeps on varying due to several reasons. And huge change, sudden change may occur. And also, in case of troposphere, which contains the mostly the water vapor, that also causes some effect on the GNSS signal. So what happens here? So one type of error, second type of error, and third type of error, it is called the multipath. And that's because the receiver is a hardware system, it has got its own noises. So here comes the signal. So you can see the atmospheric effect. And multipath is without getting the, suppose this is the GNSS receiver. Instead of getting the direct signal, the receiver gets a indirect signal. So instead of getting this one R, the receiver believes that this is R. So some extra error comes in, right? And along with that, the other problems like jamming, etc. are there. So these are the errors, and as a result, we get this type of scatter. Now the problem is, okay, a very easy read. You can search for it, or if you when you will come, we will give you this location, Introduction to GNSS, a fantastic read. Very easily, everything has been given there. So this is what we call the GNSS satellite geometry. So good geometry, so all the satellites are scattered, and the bad geometry, all the satellites are scattered in one side. Generally nowadays this does not happen, and we can see in a multi-GNSS environment the DOP value, which is a measure of the scatterness, it comes around 1, which is a very good value. Now, obviously now we have seen that there are different types of errors, and we are looking for, or we are really thriving for very good quality solution, order of centimeter or millimeter or beyond that one. So how we can do that? The obvious answer is, if you can remove the errors, you will get better solution. Your solution is being degraded due to the errors. So if you can take out the errors, your solutions would be better, right? So there are different, for this purpose, there are different GNSS positioning technique. First is called the absolute positioning. Absolute positioning, what we do generally. So this is the receiver, we are taking the data. After taking the data, we are getting solution. Obviously, it would have a poor solution. What you can see, it is showing here order of 10 meters. Nowadays, using different types of models, using dual frequency, it comes down to order of 3-4 meters. Now comes the relative positioning. Relative positioning, What is the basic idea? Instead of a single receiver, we use two receivers. One of them, this one, as the reference or the base. The second one, it is called the rover or the client. What happens? Firstly, we find out what is the exact location. There are methods like this one. What is the exact location of this base or the reference, right? So let it be x0, y0, z0. Now, when we know x0, y0, z0, at any instant of time, we are measuring x1, y1, z1. As because we know the basic or the reference, we can find out for that particular instant what is the error. So the error is x1 minus x0, right? At the same instant, within very short distance, maybe some 30-40 kilometers, another receiver, it is seeing the very same set of satellites, right? So now the delta x, that means the difference between the reference and the instantaneous value, it is being transmitted using radio or internet to this particular customer. Now this customer knows, as because they are having the same set of satellites, they are walking a very short distance, so the atmospheric condition remain more or less fixed. Only thing is their local condition is a bit different. So most of the errors, what I discussed earlier, they remains common. So the error, what this one is transmitting to this fellow, they are common. So now its location x2 minus x delta x or plus minus delta x, y2 plus minus delta x improves its location. So the methods are called GNSS, differential GNSS, which uses code-based measurement, and the other is RTK, real-time kinematic. Now you can come down here. You can see DGNSS. DGNSS can give you a little better than 1 meter accuracy up to a distance of, say, it is telling 1000 kilometer, but generally we walk up to, say, 30, 40, 50, or even 100 kilometer. And if you go to RTK, you will get even better than 10 centimeter solution, right? So this is relative positioning. And the third positioning, we call it precise point positioning. The rather probably have okay, so I've discussed here. So GNSS single point positioning, SPS or SPP, averaging, modeling, use of multi-frequency receiver. That means which can use two frequencies transmitted by the same constellation using this particular formula. Forget about this one now. So they can improve their solution. Second comes SPP. They're very simple to use. If we use multi-constellation, the quality improves. Okay. Now the differential GNSS. So this is the base. I know its exact location. Exact location, from exact location in notes, it calculates its instantaneous error and sends it to the rover of the client. Because they access the same satellite signals, the errors are common, and it uses for improvement of its own location. And differential GNSS will give you 1 meter of accuracy. Okay. Now comes the RTK. In case of the concept remains the same, only the technology changes. Instead of a code-based measurement, in case of RTK, a carrier phase-based measurement is used. Already I told that carrier phase-based measurement can give us better solution. So now the using communication link, it may be a radio, it may be internet. We will show you how to, in the hands-on session, how to do RTK, and you can get centimeter order of, say, 10 centimeter or so level accuracy within a very short distance of maybe 10-20 kilometers, like that. We have got our own base which operates 24/7 and transmits the correction message to the users. So here what happens, the very same concept, only thing is the communication over the communication link, the carrier phase based measurement is used. In the previous case, code based measurement was transmitted, errors were transmitted. Here carrier phase based measurements are transmitted. So at the rover end, a very low cost receiver, maybe some $60-70. So generally we talk about in terms of dollars, so that you keep on multiplying it by 80 or 82, like that, or for simplicity multiply it by 80. So a simple receiver of $70, it can give you centimeter, say sub 10 centimeter level accuracy. So that's the beauty of RTK. But for that, you need a software to handle that one. Secondly, you need to learn how to use it. In lot of geodetic applications still now in our country, DGNSS was the I within quote the solution, because it can give meter levels accuracy. But now the scenario globally is changing. People are going towards RTK, and as because low cost solutions, low cost devices can give you very good quality solution, people are going towards RTK more and more. That's why we want to show you how to do RTK, and we will give you the software, as because the software what we use is a open source software, from where you can download it and from where you can purchase the modules and do your own RTK. That we will try to train you. So other than this, there are augmentation systems. That means augment means supporting system. So there are different types of augmentation system, either ground-based or air-based, etc. I will not go more about this one. If time permits, someday or the other, we can discuss this one. So basically, you can see RTK. So this is the base station. The base station, the correction data, it is sending it to some radio. The radio is sending it to all other receivers who are called the rovers. The rover receives it and gets it, improves its own solution. Or the other method is the data is sent to the internet. It's called NTRIP, Network Transportation of RTCM over IP. In hands-on, it will be dealt in a much more way. So it is given to the internet, and the internet, from the internet the receiver receives it. So it gives the flexibility of we don't have to purchase the radios, and cost reduction. At the same time, whoever got the username and password, he would be able to get it. Right. Nowadays, also satellite based this type of data transmission, it is also started. In case of Madoka, if Dinesh comes, probably he will talk about Madoka or terrestrial services. So instead of getting from the radio or from the internet, directly there are satellites. That satellite will give you the correction data. So you are getting the raw data here, the correction data from the satellite, and you are improving your solution. But for that, you have to pay the service provider certain license fee. Okay. So now let us come about the precise point positioning, what we call the Formula One of the GNSS positioning. So in case of PPP, whenever we have got some time, in both the cases, RTK and DGNSS and SPP, we get the solution very fast, near real time. So this moment, I need my solution, I'm getting my solution. But PPP is a technique, precise point positioning. It is a technique where there is some latency. Latency means I'm collecting my raw data. The idea is like that. So I'm collecting the raw data. After collecting the raw data, there are so many reference points over the globe under the IGS, International GNSS Service. Right. It's a completely open, free of cost service for the benefit of the GNSS user community worldwide. And you can see now there are more than 150 stations. In India now there are 4 to 5 stations they are working. They continuously work and upload their data into some pre-designated servers. In the servers, there are some softwares which calculate the errors, right? Which calculate those errors, the satellite errors, the ionospheric errors. And after some time, maybe after 15 days, they give you back. If you want, they will supply you the correction message. So now you have got your raw data with error. You are getting the error message from some service, and using those data, you can see, you can, after some time, you can come down to the very precise solution order of few millimeters. In our case, in our laboratory, our reference point, its horizontal accuracy is 2 millimeter by 5 millimeter in the horizontal plane and less than 1 centimeter in the vertical plane. So that what we did, we collected the raw data, and after collection of the raw data, we uploaded the data into one of these services, OSPOS, OPAS, or Enercan. They are free of cost PPP services, and within a day or two, you will get back your precise location with 95% confidence. And the location is, I already told, that millimeter level precise. But the only thing is, you have to wait. You will not get real-time data. But for applications where you need to use, for example, for tectonic plate movement, etc., etc. So this data is, I would rather say, this data is quite acceptable for this one, because you do not need real-time data. Every 15 days, you want to get your data. So today's data, you will get 15 days. After 15 days, 15th January data we are getting on 1st February. 1st February data we are getting on 15th February, like that. So it is very much possible, and it's a very good tool for some of the basically scientific applications, but it is a not good tool for real life application, for example driving a car or driving a say tractor like that, because it will give you data after at least a few hours, solution after a few hours. So this is GNSS post processing. So we have taken data here, right? This is the core station, continuously operating reference station. They are collecting data, they are giving me, and then I am processing it afterwards to get my solutions. There are many softwares. For example, this is the best software, but it is very costly. Barneys, using which you can have your own raw data and your correction data fetched from the IGS network. You can process it yourself. You don't have to upload in this type of services and depend upon others. But I told you the Barney software cost around 10 lakh rupees just to purchase, and then you need extensive training, 3 or 4 trainings, that too in going to foreign places, that has to be covered by yourself only. Okay, now let me come about the GNSS application in a very brief way, because many of the applications, GNSS error sources and what are the different positioning techniques, that will be dealt by tomorrow by Dr. Ivan in a much more detail. About the receivers, I think Dinesh, we will get Dinesh, and Dinesh will be covering in much more detail about the receivers. And after that, the applications, full application part would be dealt by Dr. Ashish Shukla from ISRO, and then the atmospheric research applications would be dealt by another person from ISRO, and on the last day, the timing application would be dealt by Dr. P. Banerjee. So basically, just to have a feeling, basically, if we look into the GNSS application, we can subdivide them into basically 4 types of applications. First is position based application. It gives us solution, position solution. We can use it. The main user base is surveyors for surveying, navigating in land, air, or in ship, for monitoring of rather for monitoring of man-made and natural disasters, etc., etc. So it's a cartoon I have made. So this is a receiver. It is giving a solution, and these are the different types of solution what is possible. Second is time transfer. So if I tell you what's the time, so most of you will tell me it's okay, it's 2038. So if I now challenge you, how can you show sure that it's 2038, not 2037 or 2039? Your answer is very simple, because I have synchronized my clock with the watch that has been shown on TV like that. So that transmits the Indian Standard Time. So always timekeeping is a relative timekeeping. So nowadays, worldwide, the world time is kept using GPS or GNSS rather. Earlier, where we used to use physical transportation of the clock. You may recall that what is a second. So in an institution called Bureau International the Poison Measures, or BIPM, they keeps the world clock. So the synchronization of the clock is based on GNSS nowadays, and everybody accepts it, because not only it has got scientific uh, 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 implications, it has got legal implications, because the same time is being used in the stock markets, the basic source for money. So time transfer application. Third is atmospheric research, because the signals comes through. So let me go through one by one. So everyday GNSS applications, I think the pictures tells for themselves. What are the everyday different types of application in navigation, in road navigation, shipping, airlines, etc., etc., in road, maritime, and high precision GNSS application, monitoring of dams, continuously operating reference stations, etc., etc., flying of drones, delivery of missiles, etc. Now, different case studies during you can see developing sustainable collaboration model for implementing integrated space-based geospatial disaster management infrastructure. It is a presentation in UN Nepal workshop on application of GNSS in December 2016 in Kathmandu. I've taken just from their website. Okay, though I was present there. So developing a semi dynamic datum for Nepal after 25 Gorkha earthquake. Uh, it's from New Zealand. Similarly, disaster management system using GNSS, a paper from Nepal. habitat suitability analysis of tigers in Chitwan district, uh, Nepal. So I think Dr. Banerjee in his second talk will talk more about what may be the possible different cases of using the GNSS position-based application. So tracking of the trucks carrying hazardous materials, tracking of persons, tracking of livestock, uh, these are all possible using GNSS. So even in case of agriculture, you will discuss one agricultural rather topic in your paper discussion. So I've given a few examples here. So for example, GNSS agriculture, I can give you some idea that you can try developing. Already we got a project from DST in the government of India for development of such a project, and it is progressing well. Intelligent transport system, driver driving pattern analysis, whether a drunk driver is driving like that, or what is the pattern of drivers in a particular region, that has been done. uh, so the location trackers, I have given some example of location trackers. So earlier we had only large this type of the GNSS modules. So we have a very large solution, and it is being transmitted to a particular mobile number, you can see. But the whole thing now has changed. It has been miniaturized. Some very critical and typical examples: influence of global navigation satellite system errors in positioning inventory, plots for tree height distribution studies, how GNSS is used for tree height distribution. Similarly, GPS technology for semi-aquatic turtle research. So they've fixed one GPS receiver on the backside of a turtle and tracking from where to where it grows, what is its movement pattern, like that. So similar examples are in disaster monitoring, uh, in tsunami monitoring, and NavIC devices for fishermen. We will show our own device, what we have come out in a much cheaper and much smaller version. More and more examples are there. Only what they tell, the only imagination, you know your location. You know your location, so you can use your location in whatever requirement you want. Real-time monitoring for fast deformations using GNSS low-cost receivers. Once again, the title or the theme of this particular workshop, or FDP. So those of my colleagues who are from the GIS background or geography background, you can look into this type of solutions and come up with new ideas. Okay, more would be discussed. Like thing, QZSS based disaster alert system. It is very similar to NavIC, but not exactly like NavIC. You need some extra hardware to be included in your hardware, what is not there. So another example, this is a case study what we made in our university, that GNSS GIS based fire preparedness. We studied the whole thing. A geospatial student, she developed this paper, that how the fire preparedness of a building, of a public building or a private building, that can be studied using GNSS. So she come up with the idea. Now the last part is the GNSS signals can be used, because we are getting signals whenever it is passing through the atmosphere. If there is any effect on that GNSS signal, it will be modified. So if we can make the modification, if we can measure the modification, we can understand something has happened in the atmosphere. So to probe the atmosphere, GNSS is a very good tool. And as I have shown you, that now from every direction of the sky, we are getting satellite signals. So it is very much possible to probe every direction. So at any point of time, you can say, there are completely free of cost, nearly 50 sources are there to probe the atmosphere, and lots of people, they work with this one. So the other science applications, which would be dealt more by, I think, by Dr. Saurabh Das, it is called GNSS radio occultation. For many of it's a new topic which is coming up fast. GNSS reflectometry, by measuring the direct signal and the reference signal, can we measure the height of the waves, or the soil moisture content, right? So this is a very new topic which is coming up very fast, and many people are working on this one. In case of NavIC, because we have got both L and S band signals, so people are interested to use this one. So once again, similarly, the direct signal and signal reflected from the ice cover. So is there any difference between the quality? And if we can find out the quality, how we can measure the depth of the ice in a very simple way using two antennas together. So using UAVs, they're measuring the heights of the trees using the GNSS signal. So lots and lots of application are coming up. Another important topic is integrating GNSS with other sensors like the instrumental navigation system or inertial navigation system. So for example, you can see here when the vehicle is in an open condition, it is using GNSS. When it is obstructed, the INS takes over and guides it. So they're working in a mutually complementary way, and thus GNSS INSS integration is another very important and very interesting topic which is coming up. Now, to answer my question, which I raised a long time ago, that why so many players? So why? I was doing a course on cybersecurity in Coursera, but it was being offered by IBM. So they started the question that why the worst, rather the worst bank robber in America. He was asked in the court, why you are robbing the bank? His answer was very simple, because because money is there. Here also, the very same applies. Why so many systems? Because money is there. If you look into it is the GNSS market report. It is the older version, 2019. In 2022, just now they have released the last version, issue 7. We will share with you those who are interested. It's a very worth reading for understanding the whole GNSS scenario. So what they're telling, between 2019 and 2029, the GNSS market have seen the total the business volume is shown to be 2525 billion euros. So it's billion multiplied by 2525 into 80 billion rupees. So the world market is so large. And you, so this is the consumer solution, that is means handheld devices, and railroad solution. If you take only the chunk of the other solution, that also becomes 170 billion euros. That means 170 into nearly 82 or 84. So it's a huge market, and everybody wants that. Uh, let us develop our own ecosystem, so that our technology, our electronics, our software is let it be used by our countrymen, and if possible, let us export it to other countries, so that there may be a very strong business vertical. Looking into that, that is one point. The other point, what sometimes becomes sublime, that is every country. Some of you may be knowing the history behind development of NavIC. That when the Kargil was going on, the Indian Defense Forces reported to the government that many times GPS signals were being denied to them. Okay, so they could not find out their own location in a unknown territory. That's very serious, which has got very serious implications during the war. So what the government planned, they planned that, okay, let us develop our own system. From that it began. So to have self-reliance in case of defense, self-reliance, uh, no dependency on other system. That is one point. But the other point is, which is you cannot ignore it. That's a huge global market which is open for everybody to explore. And if you go through by this through this particular document, it is written there between this time, that is 2019 to 2029, the Southeast Asia region is the have the highest potential for the development of the GNSS industry as a whole. So that answers my question, that why so many players, everybody is trying to develop their own system. Already 6 systems are there. Along with that, cases, Korea is trying to, South Korea is developing their own system. Also, the Arabian countries are trying to develop their own system. This is the answer, that everybody wants to have a chunk of this very large business volume. And on the other hand, it tells us that it has got immense potential. That's why the market projection is like that. But interestingly, you can see the people from the geomatics, you can see 2.4% of the 170 billion market. But interestingly, or unfortunately, in our country, this particular technology is not that explored. There are a lot of people. lot of people working on the science aspects of it, lot of people doing extremely good research, whom with whom you will, many of whom you will meet. But application development for real life application and taking it to the market as a product, that is still lagging behind. Only there are a handful of industries. When I was searching for some industry, rather speaker from industry, I got a few from Bangalore, like that, few from Delhi. So it is very hard to support their travel cost down to the down to this place. But fortunately, we got two persons who are currently, although they are placed in Bangalore, one of them placed in Bangalore, he is in Kolkata, and the other person, he is permanently now in Kolkata. So we could give you the flavor from the industry. So, but so many industries are possible. So many applications are possible. That's why we wanted to take up this course, or take up this program, so that we can give some idea to the young researchers and also to the mature researchers, that along with their regular research, if they can spare some time for utilizing this excellent technology for application development. And what are the market macro trends for smart cities, utilities, transport, connected device, consumer electronics, healthcare, intelligent buildings, manufacturing and supply chain, retail and leisure, along with drones and the UAVs. So huge market is there. For example, M Health, if time permits, in the next slot, I will talk about M Health, which is a game changer. Before 2020 pandemic, we had not much, rather I would say, believe about the mobile health. But now mobile health in many cases have saved lives and saving lives. So, but every time the location of the health caregivers and the location of the particular party, that means location of the patient, they're very important to get them connected in the shortest route, in the shortest time. So there comes the need for use of GNSS, and a huge market is coming up for IoT applications. Dr. Banerjee would talk about the IoT, robotics, and the applications of GNSS. Now, the last part, the GNSS on Android smartphones. All the Android smartphones, they're equipped with a GNSS chip. And in much detail, I will talk in my next week talk, and try to show you how, using your own whatever smartphone you have with you, you can use it as a GNSS receiver without spending an extra dime. You can collect data, you can use it for your own purpose. Very recently, I will share one paper also with you, how to get the apps. So there are the different types of apps, how to get those apps and use it for data collection. That we will make you learn through the workshop method, and you will collect data and process it yourself. And so there are many apps, beautiful apps, and more resources I will on mobile phones, so that day I will cover this one. And there are many NavIC enable Android phones. Uh, Still now we could not judge how good they are behaving, but I think there are many researchers who can do along with us this type of judgment of searching the how good the NavIC enabled phones are receiving. And another question what I get whenever I present there: will older devices receive NavIC support through a software patch or update? The answer is no. You need a new phone. Uh, Now, finally, the issues. The finally issues are, we need very good quality solution, obviously at a low cost. That is possible. That is, we need secured navigation, time, and position. We need uh, resilient. We need everywhere, and we want to stop the vulnerability. A very serious issue, unintended issue, is unintentional and intentional interference. For example, this type of device, which a few days ago, in our country, keeping and using this type of device by government rule, it is completely prohibited. But believe me, I have with me uh, three this type of devices, and I have purchased it simply in open market for a cost around 600 to 800 rupees, like that. Okay, so I can tell you one interesting story. The story goes like that. Some years ago, in US, New York, not New York, NEWARK, in New York airport, they were finding that all their GPS receivers, they were being off. around 9:30 to 10 o'clock every day. So they were searching for the reason. They were searching for the reason. And what they came up that during that time, one trucker with a large truck, he used to pass by the side road which passes through the airport. And he uses this type of jammer. And it completely jammed the rather GNSS scenario, and you will get no solution. And at the same time, another problem is spoofing. Spoofing is uh, 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 mm, suppose I'm walking in Bardhaman, but somebody is transmitting a signal, GPS-like signal, what my receiver picks up and shows that not no no I'm not in Bardhaman. I'm at Kolkata. That type of problem, it's called spoofing. Spoofing is fully intentional, but jamming may or may not be intentional. Okay, so how we can get so you can see the Russia jammed GPS signals during NATO military exercise and during the ongoing Russia-Ukraine war, there are many reports that Russia completely jammed the Ukraine airspace, so many of their drones are not working. FCC finds operator of GPS jammer that affected New York Airport Jiba. So this is the report which I was talking about. So GPS jamming and proofing, yes, spoofing. So how to get rid of this one? Basically for defense purposes. So that is another, I would rather say, much open challenge. I know one of the leaders, industry leaders in India, Wing Commander Madhura, he's present here. They are working on this one. And the trends are compact multi-GNSS, multi-frequency, RTK-enabled GNSS NavIC modules are coming up. Dual frequency enabled Android device, which are coming up, which will change the game we expect. Low power GNSS modules for IoT. So we don't have to put electrical connection, only a button battery will be sufficient for a few days. Interference jamming and jamming mitigation techniques, what I already told. Regional global RTK PPP service from space. We will talk about more during some of the rather sessions. And finally, what I told that the terrestrial connection from the satellite, we are instead of getting the terrestrial system either through radio or through internet, we are using satellites for connection data service at a very low cost. Okay, so these are the basically top market trends, the opportunities for researchers and students. I think we will discuss it. So I have shown it. The further reading. So these are the final reading. I will share this PPT with you so that you can read it and come up as you like. You can download. Most of the things are free to download. You can download and read for your own convenience. So for now, thank you very much for the whole team here. You can see the full team, GNSS laboratory team here. Uh, Thank you very much for lending me your ears. So now, once again, I will take some, it is 21 now. So let us take 10 minutes break and we will start once again at 21:10. So take up a few questions and your comments on some discussions if you like. Okay, so first of all, let me make the recording off.